Hello there. We're back again. We're taking a look at logarithmic functions for calculus. This is just a review, so I hope to make this on the short side. We shall see. Logarithmic functions. So the first thing I'm going to do is make sure that I can use a pen here. There we go. Let me check it out. Looks like we're a go. All right. And we'll check the actual pen itself. Good there too. All right. Before we get any further, I could ask you to stand up and say this out loud. Oops. I need to get better at writing, I guess. Okay, the important phrase to remember is logarithms are exponents. Logarithms are not something exotic you've never heard of before. Logarithms are just exponents, and in the last lesson we talked about exponents, and you've used those for years, so let's move on. They're closely related. Yes, I would say so. Not only that, but they're inverses of each other. And there we go. That means if we use an exponential followed by a logarithm, we end up with the same number we started with. Or conversely, if we start with the logarithm and then use an exponential function on it, we end up with the same number. That's what inverses are. Go from x to another value and back again to the original x. So we're going to look first at the inverse functions since these two are so closely related. Logarithmic function is defined as the inverse of an exponential function, but important enough that it must be thought of as an individual function. Sometimes we need logarithms and sometimes we don't. Many of those are important for solving problems that would be much more difficult with just straight exponents. The Richter scale, for example, you've heard of that when earthquakes are reported. You've heard of the decibel scale. How loud is something, say at a football game, or a rock concert, or doubling in half-life for an exponential change. This is the time. Let's see, where is my cursor? Down here. There we go. This is the time it takes for something to double, and this is in years, seconds, minutes, or whatever it is. Half-life means you go from an original amount to only half of what before. But you're still talking about time that it takes for that to happen. One-to-one functions. This is important because if functions are not one-to-one, they can't have inverses. So, for example, you can see this first one over here is a function because if you draw any vertical line, it never crosses the x-axis, or never crossed the graph more than once. Also, not only that, and I'm not going to change colors on you, but if you drew horizontal lines, it never crosses the graph of that function more than once. That's not only a function, but a one-to-one function. It passes the vertical line test and the horizontal line test. However, let's go over here to this other one. Here we go. Now, first of all, this is a function. There's our vertical line test. It never crosses more than once, but this is a big one. If we draw this horizontal line, or the one that they've drawn here, it crosses it at two different places. It is a function, but not 1 to 1. For f and g, every domain corresponds to exactly 1. That means it's a function. But the range value of 2 corresponds to only one domain value, 4, in f. Whereas in g, the range value corresponds to both -4 and 4. And that's what makes it not a one-to-one function. So f is 1 to 1. It passes both tests. G is not, because it passes the vertical line test, meaning it's a function, but not the horizontal line test, so it's not a one-to-one function. One-to-one, well, if you think of functions as being fantastic equations, well, one-to-one functions are even better because they have inverses. So, a couple of things for you to think about. First of all, we're talking about continuous functions. That means something that doesn't jump and go to a different place, has no holes in it, and if that is either increasing or decreasing as we go from left to right, then it's 1 to 1. So if you have a graph like this, and you're starting somewhere down here, for example, if it either goes up all the time or down all the time, then it's 1 to 1. But if it goes up sometimes, and down sometimes, and up sometimes, it's not 1 to 1. In fact, we can create a horizontal line test. It failed. It goes through it 3 different places for that particular horizontal line. So here are examples, and you can take a look at, pause if you like, see why the first one is not only a function, but 1 to 1, and the second one is a function, but not 1 to 1. So this one over here is not going to have, does not have an inverse. And I think it's appropriate to put a frowny face on that, because having an inverse is very nice. So what is the inverse of a function? It's a 1 to 1, then it has an inverse. And it's formed by interchanging the independent and dependent values. What does that mean? It means if you take a function which has x and y values, if you take all of those ordered pairs and swap the two like this, it's still a function. It's not only a function, but it's the inverse of the original one. Oops, meant to draw it this way. Got it? So each point, if you swap the x and y values, is a point on the graph of the inverse. It's not the 1 to 1, it does not have an inverse. I think I've said that enough times. Logarithmic functions. So here's a real simple example. Most books, I think, start with this example, y equals 2 to the x. Notice something different about this one. The x is in the exponent. What we're familiar with is x being the base. This is different. That's what makes it an exponential function, because the x value is in the exponent. And because of that, it's also going to be 1 to 1. The inverse exists then, and if we take this function right here, this formula, this equation, and switch the x's and y's, switch the x with the y, this is what we have. And we've got an inverse of the original function f. And this one is noted by having a -1 where you would normally see an exponent. But since f is a function, this -1 means inverse as opposed to 1 over f. So this would be the logarithm function with base 2. Base 2, why that? Well, there's the base right there. And the way you could write it is y equals log of x, and you always put the base as a small number right to the right of the log name. And that's only true if you can write this. Now, how do you remember how to write this? All right, this is what you do. If you take a look at this equation right here, if you want to rewrite this in this form over here, the key that I give is always start with the base. Number 1, start with the base. And number 2, remember that logarithms are exponents. If you remember that, you'll be able to convert this. So if I look at this equation, start with the base. So I'll write down 2. Second, what's the exponent? Well, this part right here is an exponent. And since these are equal, y is the exponent. So there's y because it's the exponent. Logarithms are exponents. Now, what goes over here? Well, there's only one thing left, the x. Bingo. Just like that. Start with the base, put the exponent up there, and the remaining number is the result of taking 2 to the y power. That's all there is to it. Start with the base, put the exponent in, and you've got one piece remaining. Put it where it belongs. So these two are equivalent statements. That means for us that if you have a statement like this, and you find it's hard to figure out what x or y is, you can switch it from a logarithm statement to an exponent statement. You may have just beaten it. Another thing to remember is that those two functions, the function and the inverse, are reflections of each other. And the reflections around y equals x. So what does that mean? Well, before we get an x and y axis all cluttered, here's the x and y axis. This is what y equals x looks like. Y equals x. Now what that says is the reflection. It means if you've got a function that you're graphing over here, see on the right side, that if you put a mirror down at y equals x, you would see a picture of it in the mirror on this side, a reflection of it. Now here are some examples. Sort of one example, sort of two examples. We start with this exponential function right here. And that function looks like this. Notice that the base is 2. And we put various numbers in for the x. You can use our calculator. Just put the 2 in, put the x where the exponent should be. In other words, put the -3, the -2, -1, and so on, and hit enter and see what that exponent gives you for a y value. -2 gives you 1/4, -1 gives you 1/2, 0 gives you 1, and so on. And you can graph them. And the same thing is true with the logarithmic function. And one thing you can do is you can take your function written like this, and you can take the x values here and figure out what the y values are that match up with it. So here's a picture of both those functions. This right here is the original exponential function. This over here is the logarithmic function right there. Notice that if you took this graph and flipped it along y equals x, you would end up with a blue graph, and vice versa. Take the blue graph, flip it over y equals x, and you get the red graph. One-to-one functions are have inverses. So you start with the exponential function. The inverse is the logarithm. And one more time, I probably won't stop saying this, but remember, logarithms are exponents. That's key to your knowing how to work with logarithms. Now, one or two other things that you need to keep in mind. Remember I said that the base was very, very important. The base is your friend. Well, two things you need to know about the base b. First of all, it has to be positive. You do not put a negative number where the base is. The second thing you need to remember is that you don't put a 1 where the b is. Now, there's only one reason for that. And let's take a look at this simple one right here. We had this one before, and there's a logarithm function with the base 2. But what happens if I have a second one? Let's call this y sub 1, this one y sub 2, different functions, and make this 1 to the x power. Well, the silly thing about this one is that when you make up a set of x and y coordinates, no matter what you put down here, this will always be a 1. 1 times 1 is 1. 1 times 1 times 1 equals 1, and so on. So, although it's not illegal, but it's pretty silly. So, b has to be positive, and we leave out using 1 because that's silly. Two things. So, this is the number, this whole thing is the number that b would have to have as an exponent to end up with an x. We'll do it again. Start with the base. What's the exponent? Well, the logarithms are, or is, right here. And what's it equal to? What's the only number that I haven't put down yet? The x. Logarithms are exponents, remember that. The domain is all positive real numbers. And it's also the range of the exponential function. Remember, they're inverses, so that makes sense. The domain and range swap places when you go to the inverse. So there are two functions, an exponential one and the logarithmic one. They reflect around the y equals x, giving you the inverse. Now, take a look at these three. Now, the first thing, some of you are going to jump to conclusions and think, what am I supposed to do with this? Nothing. All you're supposed to do is change the look of this. This is some practice, but remember, always start with the base. So 5 is the base because that's the number down here and y is at the base, one thing you can remember is the number that's lower than any of the other two is the base. It's like an abasement. What's the exponent? Well, remember, I'm harping on logarithms are exponents, so there's the exponent. So we have 5 to the third. There's the base, there's the exponent. What's it equal to? Well, what number have I not written yet? 125. And of course that's true. 5 cubed is 125. 5 times 5 times 5. All right, next one. Can you pause it and do this? Okay, are you back? All right, there's my base. Always start with the base. Now remember, logarithms are exponents. There's the exponent. What's it equal to? The number that I haven't written down yet. It's that simple. So looking at this is a way of saying 4 to what power would give you this number right here. The base to what power will give you the number that's right here. So let's try it again. So on this one, 3 is obviously at the base. It's in the basement. This is the exponent over here. And what's it equal to? 1 over 27. And of course, if you look at this, that says, okay, I could write this as 1 over 3 to the third, and there's your 1 over 27 again. It's very important to be able to switch between the two. This is going from logarithms to exponents. Just a different representation of saying the same thing. Next, let's switch these to logarithms. We're doing just the opposite. So what am I going to do? I want to change it to logarithmic form. So what I can do first on this one is say, okay, I want to get a logarithmic form. So log, well, what's the base? Well, there's the base right there, 3. So I'll put a 3 in the lowest position. What's the base's exponent? The exponent is, oops, sorry. Boy, that was terrible, wasn't it? There's the exponent right there. So log base 3, there's the exponent, and the number that I just wrote over is the 1 over 9. Base, exponent, the number you get. Let's see if I can keep from screwing up this one. So I want to write it as a logarithm. What's the base? 125. So put a 125 in the basement. It is an exponent. What's the exponent? 2 over 3. And what number goes here? 25. And you can write it again. You can make 25 to the 2/3, 125 to the 2/3, put that in your calculator and double check. But an easy way would be to check this would be this means cube root. So the cube root of 125 is 5. Then square it, there's your 25. We're in business. So now one more. We want something that looks like a logarithm. So there's the log. What's the base? Right there. So put the 2 where the base belongs. Because remember, there are a lot of different logarithmic bases. You can choose anything you want to as long as it's a positive number. And not 1. That would be silly. Now, what's it equal to? Over here, logarithms are exponents. So the exponent goes here, which means the 256 goes there, and you've got it in logarithmic form. You're going backwards and you're going forwards. Next, now this is what we were really getting to. The other was a little bit of playing around to make sure we're familiar with how we can go back and forth. Sorry, it was Mountain Dew time. All right, so here's your equation. Now we can't solve it the way it is. So what we're going to do is we're going to convert it to exponential form. Where do we start? We start with the base, b. What's the exponent? Well, remember, logarithms are exponents. So there's the exponent. What's it equal to? Well, the number I haven't written down yet is 100. And you can tell right away. B squared equals 100. B is 10. Of course, you always want to take this and double check and make sure that works. In fact, there's another reason why you should double check this particular one, the first one, to check and see whether you can take common logarithms or other logarithms other than natural logarithm. So find out where this is on your calculator. Find out how you can put in different bases, because this one had a base of 10, but they won't all be. And how you can put in what the argument is and see if you get the 2. So it might look something like this on your calculator, for example. You might have a blank there, and you might have a blank here that you can fill in and see if you get that too. Okay. Next one. You know how to start. Why don't you pause this and see if you can solve for yourself. Give you a second. See you in a moment. All right, I see you're back. Well, 6 is the base, so I'll start with that. Since logarithms are exponents, 5 goes up here. And what do I get? I'm supposed to get an x. And what do I get? All I have to do is take 6 times itself 5 times. And let's see what we get. Write in exponential form, and there's our x. 7,776 is the missing number up here. Just by converting it from logarithmic form to exponential form, the whole thing becomes child's play, literally. Here are some good properties. I would suggest you write these down on a 3x5 card or 4x6 card or somewhere where you won't lose it for a few days, because some of these are very good to remember. I'm just going to go through them very quickly because we're just nearing halfway. First of all, this one says, remember, these are logarithms. It says, what would b need as an exponent to give you 1? Of course, 0. b to what gives you the 1? That's a good one to remember. The second one, this says, what does b need as an exponent so you end up with b? Well, of course, 1. Don't get scared. Just remember, this says, what does b need as an exponent? So you end up with what's right there. Next one. This one says, this is almost the same, but it looks confusing. But if you use the words that I just used, maybe it'll pop out once you say it 3 or 4 times. Always start at the base, remember. b to what power is going to give you b to the x? Well, there's b to the x. That's what you're going to get, so it has to be an x. Number 4. Notice the base here is b in the exponential. The base here is b in the logarithm. And if you remember, they're inverses. So using an exponent, then using a logarithm means you're going to end up with the same number all over again. Exponent, and then the logarithm in either order, and you're going to end up with x all over again. Those are inverses of each other. Next one. Now you're going to use these even more. The ones over here, you can figure those out as you go, but it's handy to know those real quickly. The next one, we've got the logarithm, base b, of a product, m times n. Another way of writing this, some will call it a simplified form, because there's no multiplication over here, is if you think about what happens with your exponents, if you have a to the 6th times a to the 8th, you end up with a to the 14th, also known as a to the 6th plus 8. So multiplication back here means you're going to have the sum of the two individual logarithms. And it works like this. So make sure you're able to take this with a product and split it into two separated by a plus. Now if you get that down, the next part is not too hard. Instead of a product here, we have a quotient. Since we had a plus for the product, you might guess we'd have a subtraction for the quotient. We still have an m and n, positive numbers. The quotient can be given as the difference of the two logarithms, and the product can be given as the sum of the two logarithms. Get some practice so it becomes automatic. Next, now these are very similar to each other. Once you get it down, oh yes, I've got that. The next one, a little bit different. This one says, okay, what do I get for a logarithm, or what is going to be the exponent if I have m, some number, to the p power? And p does not represent a prime, it's just a number, a real number. Now, the way I remember this is, if I've got a number here and it has an exponent, I slide this exponent out front. So I end up with p in the front and log base b of m on the right-hand side. Whatever works for you. If you think of another one, I'd like to hear it. But that's the way I work it. Next. Here we've got two logarithms. But notice the logarithms are the same. What does that mean? Well, one more time, logarithms are exponents. So this says, what does b need as an exponent to give me an m? This says, what does b need as an exponent to give me n? Well, if you end up with the same number, you must have started with the same exponent, right? And that means these numbers have to be the same if the exponents are the same. Remember, these are exponents, and the only way that's going to happen, b to a power, if these are the same, then the x and the y have to have been the same, and these two originals are the same. Okay, here's another test. This is sort of preparing you for solving interesting equations that have to do with logarithms. What we'll do here is we'll practice splitting this up into simpler expressions. What we'll notice first is, of course, the b, there we go. Remember, b is the base. So one of the first things I can do, it doesn't have to be in the same order as someone else does, But I notice that I've got a quotient because of that fraction bar. So the first thing I can do is I can rewrite that as log xy to the base b minus, because I've got the quotient, log base b of what's in the denominator, tz. Now, I can actually simplify that. If you sneak back previously, or if you've written this down, notice I've got the logarithm of a product. Well, that's the sum of the exponents. So if I look at just this part right here, I can split that up into log base b of x plus, because it's a product, log base b of y. And that's the same thing as this. Minus. Now I'm going to put these in parentheses because minus sometimes can mess things up if you're not careful. I'm going to do the same type of thing with this one. I've got t times z, so I'm going to have the sum of the two logarithms. So logarithm base b of t, what? Did I hear you say plus? Good. Logarithm base b of z. This is all of that. Now, before we stop though, notice we've got a minus in front of the second set of parentheses or brackets. So my final answer would look like this: log base b of x plus log base b of y minus log base b of t minus log base b of z. And that would be your simpler form because there's no division there, there's no multiplication there, everything is in addition and subtraction. Next, let's try this one. You think you can do it before I can do it? Okay, go ahead. Pause it, come back. I'll be here. All right, you're back. And what I've got here, notice that I've got some number, that's all I'm going to call it, blob. A logarithm of a blob to the fourth power. So what I'm going to do is I'm going to bring this 4 out front. So I'll rewrite it as 4 log base b of xy. Now, do you know what I'm going to do next? I'll give you a hint. Remember, this is one number right now, but I'm going to split this into the sum of two logarithms. So I'll have 4 log base b of x plus, because it's a multiplication, log base b of y. And we can also finish up 4 log base b of x plus 4 log base b of y. And there's our simpler form. Next, can we do this one? All right, let's see. First of all, I see an exponential form. Maybe if I switch it to a logarithm form, it'll be easier. Let's see. Well, what I'm going to do is I'm going to start with the base, of course, as I mentioned before, the base. And since I want to work with this, I'm just going to call this y temporarily. So what is the exponent for the 3? Well, the exponent is this. So I'm going to have 3 as my base for my logarithm. The exponent is x log base 3 of b. and I've got y there. Now what can I do? Let's see. Both of these are log base 3. So if I take the log base 3 of this, and I get the same thing as log base 3 of this, they must be the same. But I'm going to have to fix one thing first. I'm going to rewrite this one, log base 3, of y, and I'm going to bring this x up here. Log base 3 of b to the x. I'm reversing that procedure that I had earlier when I brought the x out front. Now I'm bringing it back up. Now, both of these are log base 3, so this and this must be the same number. Y equals b to the x. And I'm not sure what they had in mind, but that's certainly a simpler form. Let's see what they had in mind. So they wrote this, which of course just means they took, took this and brought it up to the top. I just did it a little bit differently. And so they said this part right here is the same as b to the x. All right, so I guess they did have the same thing in mind. Let's try this one. This one has an interesting equation. This gives us a chance to use some of those properties. So here's our equation from there onward. Notice that we're adding exponents, and that means we're multiplying the original numbers. So I can rewrite this part as log base 4 of x plus 6 times x minus 6 equals 3. Now, where can I go from here? Back to the base. 4 to what power? Well, logarithms are exponents. So the exponent is 3. And what's it equal to? The rest of it. X squared minus 36. All I did was, you would say, FOIL that. But it will give you a difference of squares. So you could do that too. This is a 64. Equals x squared minus 36. Subtract the 64 from both sides, I'll get the 0. And we want the 0 because we've got a quadratic. And when I subtract the 64 from both sides, I've got x squared minus 100. And we're just going to work ourselves back. Factor that because it's a difference of squares. Equals 0. So x plus 10 equals 0. And x minus 10 equals 0. So x equals negative 10. X equals positive 10. Now, I bet you think we've got 2 answers for this. Well, that might seem obvious. But remember the old idea of checking your equation when you're finished? This really applies to logarithms. Because let's take this negative 10 that we've got down here and see if that works. In particular, if I put a negative 10 in here, that becomes a negative 16, or more to the point, I'll be looking at log base 4 of a negative 16. No. We can't take logarithms of negative numbers. They have to be positive. That means that this answer we got down here is disqualified. Better yet, we think 10 is a good solution, but you better check it. Log base 4, 10 plus 6 is 16, plus log base 4 of 10 minus 6 is a 4. And we're supposed to get a 3. Let's see. So remember what this means. 4 to what power gives you 16? 2. That's where knowing the definition and what this logarithm actually means, how it works out, can make it really easy. You don't have to put it in your calculator. That's pretty silly, really, because this says, what exponent does 4 need to give us 16? And over here, what exponent does 4 need to give us a 4? Pretty silly, right? 3. And this one works. So we get a red star for this one. So here is our solution. X equals 10. Let's see how messy I can make this. All right. 2 real simple things to remember. We can use any positive base except for 1, because 1 wouldn't make any sense. But there are 2 that are used very, very often. E, Euler's number, and 10, because that's the base that we use almost every day. Remember, E is 2.718, etc. It's a transcendental number. I mentioned that last time. And of course, you know 10. If you don't, look at your 2 hands and count the fingers, okay? All right. Common logarithms have base 10. Common logarithms, base 10. As a matter of fact, if you see something like this, if it doesn't show a base, it's automatically 10. That makes it a common logarithm. If they want any other base, they'll specifically write that base down here. Second, if they want that base of, say, 172, suppose they want it to be E. Well, this is used so much that we actually have a shortcut for that. And we call it the natural logarithm because E happens so much in nature. All right, let's move on here. So, just a note right in the center here. Without the base means it does have a base, and that's a 10. Common logarithm, base 10. Natural logarithms have base E. So these 2 things mean the same thing. ln and log to the base E are saying the same thing. You might very quickly become familiar with log and ln on your calculators so you can access them quickly. Some of them have ln for a second function, but whatever it is, you find out what works best on what works on your calculator. All right, we've got another equation here. Let's see what we can do with this one. So we've got the natural logarithm here, and we want to get familiar with playing with this. We've worked with general logarithms, but remember, they are logarithms, which means they are exponents. Now we're subtracting those logarithms, so that means we're subtracting exponents. So what we've got is a natural logarithm of x plus 1 times let me do this again. Subtracting, so it's natural logarithm of x plus 1. It's minus means division. So we'll have the x from here in the bottom. And We've just rewritten the left-hand side, so it's still equal to 1. So is that as far as we can go? Of course not. The natural logarithm has a base e, and the natural logarithm is an exponent. So this can be rewritten as e, there's my exponent, logarithms are exponents, e to the 1 power equals x plus 1 over x. Now you could just put 2.718 whatever in here because that's what e represents, but let's leave the e there for the time being. If we want to solve this as a regular equation, we'll multiply both sides by x. So we've got e to the x equals x plus 1. Remember, this is a regular equation. Don't get freaked out. So we want to find out what x is. All right, the x terms need to be on one side. So I'm going to bring the x's to this side, the x's to the side. So x minus ex over here, and we'll put the minus 1 there. The next trick is I'm going to factor out the x. We've done this, something similar like this before. 1 minus e. If you don't see that immediately, remultiply it, you'll see what it is. We haven't done anything, so that's still negative 1. Now, how do I solve that? Well, of course, divide both sides by 1 minus e. So I end up with x there, and 1 minus e there. Bingo. You got it. You might prefer, or maybe if you check the back of the book or the solution manual, for example, see, there we go. You might want to take this, since there's a minus 1 in the top and 1 minus e in the bottom, you could multiply top and bottom by minus 1 and write x as 1 over e minus 1. It looks a little bit more elegant, doesn't it? And then if you needed an exact value, put it in the calculator and get your exact answer. So get familiar with your log key and your natural log key. You might also want to see if your calculator has a common log function and maybe a different one that looks like this. Explore your calculator and see what you've got. A natural logarithm function, no problem. This is only necessary if you end up with some different kind of base that's not a 10 or an e. So check to see what you need to do on your calculator. Do you put the number in, then hit the log, or put the log in, then put the number in and hit enter? You have to know how your calculator works. Okay. All right. They put the answers here already, but try these for yourself. Make sure you know how to do this on your calculator so you end up with this answer. And make sure you can put this in your calculator. So you're doing once with a common log to make sure you know how to do that. Once with a natural log, make sure you end up with this. And then try that and see what happens. I'm not going to tell you what happens, just do it. All right, there you go. Log of 5287. Those are what you should get from those two results. And then the third one. You shouldn't have fallen for that. Honestly, did you really fall for that? You don't take logs, natural logs or otherwise, at negative numbers. So of course it said error. what would you expect it to say? See, where's my, there we go. Don't let this happen to you. As soon as you see something like this, a negative number being given to your log function, don't even do it. Be nice to your calculator, okay? Next, can you solve this? Pause it, come back if you like. I would rather you did that. Give it a shot. So, you can't solve it just like that. So we'll convert that to an exponential. Notice there's no base showing here, so it's automatically 10. And you always start with the base, 10. What's the exponent? Logarithms are exponents, negative 1.864. Hit enter. Use 4 decimal places. By the way, when in doubt, just use 4 decimal places, okay? And there you go. There's your answer. 4 decimal places. Next, can you do that one? This is basically the same. The only difference here is that for this one, our base, of course, is e because this is a natural logarithm. So e to this power equals x. Write that down. Eventually, you can do it in your head sometimes. Just be careful. So write that in exponential form. Run to your calculator. I know you have to run to your calculator. I do too for that one. Can you do this one? Well, let's see. This one is a problem. You've got x in the exponent. How can I get it out of there? Well, logarithms, of course. And notice what the base is. You always go to the base. So what we want is a common logarithm, one that has base 10. Now, what is the exponent? What's the number over here? Well, logarithms are exponents, right? There's my exponent right there. Where's the 15 go? Right there. And all I have to do is ask my calculator, what is the logarithm of 15 to the base 10? Or what's the common logarithm of 15? There you go. Which is what you'd expect. 10 to what power gives you 15? In particular, that's this number right here. Next, can you do this one? Take the natural logarithm on both sides. Very easy. You don't have an answer yet, but don't worry about it. Bring that x out front because it's an exponent inside your natural logarithm function. Now all you have to do is divide both sides by the natural logarithm of 5 and then run to your calculator. Notice, for example, very important, the natural logarithm of 11 over the natural logarithm of 5, which is what you were supposed to do. You might be tempted to do this. In fact, I dare you to get those two answers. They are not the same. So don't try to take a shortcut. You have to put the natural logarithm of 11 on the top, the natural logarithm of 5 on the bottom. No shortcut for this one. Now, what if you have to change base? This probably is something you won't have to do, but just in case. Now, here's the exponential version of it. We can take the logarithm of both sides. Bring that y out front. Now notice you got the 10 as the base on both sides. So you can do it like this. If you need that, that's like the one we worked a minute ago. Remember, we can't take x over b and then take the logarithm of that. Okay, we're getting toward the end, but since you will be working, if you're working in business, investments would be very important. And what you might be interested in is doubling times. In other words, if you put $1,000 in the bank, how much time has to go by until you have twice as much money as you had to begin with? That's the doubling time. And exponential growth models have a fixed doubling time. An investment with a shorter doubling time has a higher rate of return because it doesn't take as long for your 1,000 to turn into 2,000. Logarithms make this much easier. Otherwise, you'd have to do a trial and error until you finally got the time that would give you double the amount. So how could you do that? Well, if we have a rate of 15%, compounded annually, now notice it doesn't say continuous interest. So we have to use this one when we don't see this one's not continuous interest. So we have to use this formula instead. Put the numbers in there. One note, I think I mentioned it in the other one. Typically, this number right here is represented by an n instead. So you might see that in most formulas here and here. Remember, it's two places. Just put those numbers in your equation. What this means is you started with p, you ended up with twice as much. Just put it in your equation. One nice thing is you can divide both sides by p. Did you expect that? Okay. Now what can you do? T is in the exponent. Take the logarithm both sides. And the easiest one is to use the natural logarithm. So do that. Divide both sides by that natural logarithm of 1.15. Remember that t, where am I here? Remember we brought that t out front. It's one of the properties of logarithms. So all I have to do is divide both sides by that and then put it in my calculator the correct way, and I'll get how long it takes any amount to go from whatever it is to double the amount. Okay, now logarithmic regression. We haven't done this, and we're not going to do too much of that here, but I'm going to give you an idea of how this works. Whether you use a TI-84 or you use a TI-Nspire, it doesn't make a lot of difference. The number one thing you have to do is you have to put the numbers in. So for example, here are some ordered pairs. You've got numbers here, the x values, and you got the p values, which represents the price per dollar, the price of each one. So you'll put these, for example, and the TI-Nspire people I think can do something similar. So maybe put these in L1 and put these in L2. And you can use a regression equation to predict the price If we decide, or if we were able to sell 6,000, how much would we make? So put the numbers in and use this statistics calculation. Now let me stat, you get down to ln reg. Now notice it's ln reg. Where am I here? Look for this one because you're working with natural logarithms. Once you tell it to use L1, there we go, L1 and L2, and pull up this, it will give you this equation which tells you for a particular x, the 6,000 we were talking about earlier, if you put the 6,000 in here, how much would you get? So if you want to sell 6,000 screwdrivers, I can't see the result because there's something in the way on my screen. You should be able to see it on yours, or maybe not. Let's see if I can move that out of the way temporarily, just in case you can't see it. Oops, here we go. In case you can't see it. So we would need to sell them at $47 to sell 6,000 screwdrivers. Well, that's it, folks. I'm done for the night. I hope you are too. And I'll see you tomorrow. Bye.